Hello, physical systems. This is Nathan. We're going to go over the lab you guys did yesterday, and we're going to go over some new stuff, some laws from some dead guy named Isaac Newton. So first of all, I'm in my kitchen, in my pantry, and really, kitchen is the best place for any kind of science to happen, especially chemistry. But this isn't chemistry, this is physics. So let's talk about physics. So first of all, this is the first video I'm recording for you guys for our new unit of forces. Last week, you guys did something called kinematics, which is telling you about how objects move, but forces is all about why objects move. So let's just get right into it. I'm going to be going back and forth between my face and slideshow. Get there real quick. And by the way, I'm actually recording this during my tutoring session, so if a student comes in, I might turn it off for a second. So first of all, before we go too far, let's define force. Force in physics is a push or a pull. It's that simple. So if something is being pushed or pulled, we call that a force. You guys did 5 different kinds of forces yesterday in yesterday's lab. I asked you guys to move some objects and talk about, well, why do you think it moved? Now we're going to give names to those forces. So there's lots of different types of forces, even though a force is just a push or a pull. Let's give those forces some names now. Can I make this bigger? Ooh, I can. Cool. I hope that this is showing in the recording. I hope that my face is getting bigger as well. So it's going to cut off a little bit of text, but I think the bigger picture-in-picture is going to be helpful for this. So first thing I ask you guys to do is just find an object like a pen and pencil or silverware. I chose a highlighter, and I asked you guys to drop it. And I asked you guys, well, why did it fall? So I'm going to take my highlighter, and I'm going to let it fall. It fell down to the counter. So some of you guys might have already guessed this. This is called gravity. So, and yesterday you learned about gravity. Gravity is the force of attraction between any two objects with mass. Well, my highlighter has mass, and if you don't know what the other object is, it's not the floor, it's actually the entire Earth. So that attraction makes those two objects want to come together, and the highlighter didn't quite reach the Earth. It landed on the counter instead of the Earth, but that's okay. So, and by the way, stay tuned for the end if you want to hear some bonus facts about gravity. Gravity, even though we've been studying it for, humankind has been studying it for thousands of years, we still don't know how it works. You can hear scientists go on about some fancy stuff about geometry of the universe or about what I just said, masses being attracted, but we don't know why masses are attracted, and we know that objects are imbued with mass. We don't know why, and we know that those masses attract. Again, we don't know why. So stay tuned later if you want to hear some interesting facts about gravity. But anyway, when we see something fall down to the Earth or any astronomical body like the moon or the sun, we say that's caused by gravity. Next thing, I'll use my phone for this one, I asked you guys to do is I asked you guys just to pick an object like a book, something solid, something you can slide, and I asked you guys just to slide it. Okay. So I pushed it with my hand and it slid. So I asked you guys, so why did the phone move? Well, it's because I pushed it. Remember, a force is just a push or a pull. So when we just call that applied force. I applied force with my hand to make the phone move. Now, why did the phone stop? That's another question. The phone stopped because of this force called friction. And again, you also learned about friction yesterday. Friction is the force between two moving objects that opposes the motion. So I'm going to do some slow motion here. So when my phone started moving, there was motion between the phone and the counter. And remember, whenever there's two surfaces, so one surface is my phone, the other surface is the counter, and one of those surfaces in motion, friction wants to oppose that motion. So friction will make sure that my phone stops. So again, if you have two surfaces and one or both of them is moving, friction will always act in the opposite direction. Even here, hang on a second. Even with something like an ice cube, has a very, well, I couldn't get it quite slippery enough. Has a very low friction, but it still stops. If this entire surface was made of ice and I still ice on ice, it looks like it might go on forever. And I had to stop with my hand that time. Even between two pieces of ice, there's still, I missed the sink, still a very low amount of friction. Okay. So the other next experiment I had you guys do, I had you guys take two pieces of paper. I asked you to crumple one. I might have to zoom out on the camera on this one. Crumple one and keep the other one whole. And then drop both of them. Let me kind of step back a little bit. But you guys already saw that one fell slower than the other. So there we go. One fell slower. And why is that? Well, it's because of something called air resistance. So the reason why the two papers, one fell slower, one fell quicker, this ball of paper, and this paper, so this has more surface area. If you guys are going to take geometry, you'll learn about something called area. This is more surface area exposed to the air. And so this kind of catches more air as it falls down. So this doesn't catch my air, so it just kind of goes straight down. This paper kind of lofts its way down. And that's why parachutes work. I'm going to pause the video. All right, we're back here. Get back to the slideshow. And you can see I'm not using fancy editing equipment. So, talked about air resistance. The last experiment I had you guys do was I had you guys hang a string. I have a lanyard for a string. And I asked you guys to hang something. I have a weird handle. So whatever you hung on your string is fine. Or if you had a backpack strap or a purse strap, whatever. The question is, what is keeping your object, whether it was your purse or your bag or something you tied to a string, what is keeping it from falling to the ground? Well, it's the string, right? So this string is keeping the object from falling to the ground. So whenever there's like a string or a rope or maybe a chain, anything like that involved, physicists give that the name tension. So this string has tension, which means that this string is taut and tight, and the force of gravity that would otherwise make this object fall to the ground is being counteracted or balanced by all the way along this string. So every point along the string is sharing some weight of this object. That's called tension. So these 5 forces. You'll see the names come up now and again as we go through this unit. So it might be important, especially for those first 3 forces, just to take notes on knowing exactly how those things work. And there might be a few more forces that we introduce as we go on. So let's categorize these forces here. So we talked about each of these 5 forces, and something you guys read about was contact and non-contact forces. So a contact force is something that requires physical contact. Non-contact does not require physical contact. And those non-contact forces, there's not that many examples that we're going to go over in class, but there's also not that many examples in the universe in general. Those are really interesting forces. So first one we did is gravity. Gravity. The Earth is not touching the highlighter, but yet the highlighter is attracted to the Earth. So since there's no physical contact, that is in the non-contact category. Applied force, where I just pushed my phone to make it move across the counter, that is a contact force because I had to physically touch my phone. The friction between the counter and the phone, well, the 2 surfaces were in contact, so that is a contact force. Air resistance is kind of tricky for some people, but when that paper fell down, the air that is making that paper slow down has to touch the paper in order to slow it down. So air resistance is absolutely a contact force. Tension is also a little bit tricky to think about because, well, I know that the string is touching the handle, but is the string, so we would also call this contact because force is being moved along something physical, something that I can touch. So that's a contact force. So I notice that gravity is the only force in our non-contact column. Again, there aren't that many examples of non-contact forces. Another one that is not included here is magnetism. We didn't do anything, but if you think about magnets, let me grab a couple real quick. Okay, these magnets aren't actually strong enough, and I'm just going to pretend that they are. So magnets will attract each other, and they'll repel each other, but they don't have to be touching in order to work. I can grab a paperclip with a magnet, and the paperclip doesn't have to be touching the magnet. So that's called a non-contact force. These are also called field forces, by the way. Okay, so that's a review of our lab from yesterday. Let's go on and talk about Isaac's first and third laws of motion. You might notice that I'm skipping Chu. That's not because I forgot how to count. It's because Chu is a little tricky. It involves some math. More on that later. So Newton's first law of motion, CK12 says an object at rest will remain at rest and an object at motion will stay in motion unless it is acted on by an unbalanced force. Okay, so I'm going to simplify that a little bit. I'm just going to kind of change that middle part to say an object will not change its velocity unless acted upon by an unbalanced force. And remember, we said velocity is just speed with direction. So really, Newton's first law of motion just tells you that matter is lazy. So matter is what the universe is made of. Anything you can touch is made of matter. So for example, the matter in my phone is lazy. It doesn't want to do anything. So if I leave it on the counter, I can test Newton's first law right now. Actually, instead of my phone, I'm going to use this little toy car. So this toy car is pretty lazy. It does not want to change its velocity. And how much velocity does it have right now? Well, it has a velocity of 0 meters per second, 0 miles per hour, whatever you want to call it. It has a velocity of 0. It's pretty lazy. It doesn't want to change. So to get it to change, we have to give it a force, push it. It fell off. So it will not change velocity unless acted upon by an unbalanced force. And if you don't like that word unbalanced, well, you can just cross it off your mind, your little mental checklist for now. We'll come back to that word unbalanced. If you just want to think of Newton's first law as an object will not change its velocity unless acted upon by a force, that's fine. Newton's, and just an example of Newton's first law. I kind of gave an example of that. I kind of gave that first example already. But another example is when an object is in motion, it does not want to change its motion. So if I put this object in motion, it's not going to change its motion. Oh, wait a second. It changed its motion. What's that about? Well, okay, that second part. A moving object does not want to change its motion. Something has to speed it up or slow it down. So that thing that's slowing it down is, remember that example of friction. Okay, well, it didn't slow down in time there, but friction is acting between the car tires and the surface of the counter. So that's slowing the car down. If there was no friction, and we can create environments where there's practically no friction, this car would just keep on going and going and going forever. And as long as I had countertop, this car would keep on going. So that's an example of Newton's first law. Newton's third law is what I call the law of pairs. Forces act in pairs. So CK12 says every action has an equal and opposite reaction, which is kind of catchy, but what does it mean? So this is kind of what it means. Right now, I am standing on a floor. You can see my slippers. And so gravity is a force that's pulling me down, right? So according to Newton's first law, if I have a force acting on my body, I should be moving in that direction. So if gravity is pulling me down, why am I not moving down through the floor toward the center of the earth? Well, something has to be pushing me back up in order for me not to fall down. So we say the floor is pushing back on my body, is pushing me back up. So gravity is pushing me down, but the floor is pushing me back up, keeping me at a rest state. Now, you might be thinking, what do you mean the floor is pushing you up? The floor, it can't move, it can't do anything. Well, so it does. Something has to be counteracting that force of gravity, and we say that is the force of the floor. Later, we're going to be calling that the normal force. I gave you guys a couple other examples there. You guys can read them. I'm going to move on before my meeting runs out of time. Oh, actually, I'm done. So that covers forces days 1 and 2. Obviously, you guys are going to do a little bit more. You're going to read about friction. You're going to read about Newton's first and third laws a little more, do some practice. And I did tell you that I was going to tell you a little bit extra about gravity at the end here, so I will. But first of all, if you have any questions, please feel free to get a hold of me. And if you don't want to hear about gravity, you can close the video now. And you're still here, which is cool. I'm glad you're ready to learn. So gravity is interesting. First, I told you guys how we don't really know how gravity works, but gravity is actually one of the weakest forces in the universe. So again, you might think to yourself, well, what do you mean it's weak? It's keeping me to the floor, right? Well, let me just give you an example. Let me see if I can point my screen down to the right spot. And I'm going to have to kneel down a little bit. Ugh. Okay. And this is something you can try at home, by the way. I got these little pieces of paper. So we know that gravity, if you guys did your reading yesterday, you know that gravity is the force between masses that make those masses attract to each other. For example, we are all walking and resting on the earth because the mass between our bodies is attracted to the mass of the earth. I have a comb here. I have some tiny pieces of paper here. These paper has mass, very small mass, but a mass nonetheless. And a comb, not very much mass, but definitely more than these little tiny pieces of paper. So if this has mass and these pieces of paper have mass, shouldn't they be attracted to each other? And the answer is yes, but the force of gravity is so weak that no matter how close I put this comb to the paper, they're not going to attract. However, if I rub, and this works really good on dry winter days, but if I rub this comb through my hair, I can electrically charge this comb. Now this comb has a charge, and if I put it close enough to these pieces of paper, they attract. I almost got a chain of 2 going for a second. So gravity can't even pick up tiny pieces of paper with the mass of a comb, but electricity does it with no problem. Electricity is millions of times stronger than gravity, which is why it's so easy to use in electronics, but we can't use gravity in electronics or anything. Can't make machines. Well, I'll stop there. So, but anyway, so that's a pretty cool experiment. Again, if you guys need anything, email or text me, and you guys have a great day.